Alright, in case it is helpful, I want to go over the low-stakes quiz on rational exponents. So, the first problem, this is in radical form, meaning it's got the radical sign, and I want to turn it into exponential form, just so I understand how they work and the relationship between them. So, first of all, in exponential form, I'm going to contain all of the information that's given here simply as an exponent, and that's the beauty of exponents. So first of all, x is in the denominator, so I know that my exponent is negative, right, because that'll be 1 over x. And now x over here is to a certain power. First it's squared, and then I'm taking the fifth root of it. So those two ideas I could capture with two exponents, the square and the fifth root. Then I can also rewrite that, thinking the two, x to the 2/5 power, so there's my rational exponent, x to the 2/5 power. And you can see that you can also see how the exponent rules apply here. I can just multiply those two and get 2/5. Alright, so x to the 2/5 power is in the denominator, and I can rewrite that as x to the negative 2/5 power if I want to capture all of that in an exponent. So I've turned my radical form into exponential form. Now this one I'm going the other way. So I want to take all of the ideas represented here and express that in radical form. So first of all, I notice that in my parentheses is 3r. So 3r, the entire thing is raised to the 4/3 power. Now I could again rewrite this as 3r to the 4th to the 1/3 power. Right, both of those ideas are contained in that exponent, 4/3. And you can see by exponent rules I would end up multiplying those, which is where the 4/3 comes from. But if I want to break apart those ideas, then I could write it this way. Alright, so the 1/3 indicates that I have a cube root, right? Fraction exponents are roots. So I have the cube root of this thing in here, so 3r, the whole thing to the 4th, right? Not just r, but also the 3, and the cube root of all that. Alright, you could multiply the 3 to the 4th out to be 81. You could also take the cube root of 3r, and all of that is to the 4th power. That would be equivalent. Right, that would simply be saying, if I broke it up this way, with the 1/3 power inside and the 4th power outside. These two are identical, and this one looks more like that. But these two are identical, and both would be fine. Okay, moving on. From here on out, we're simplifying. So positive exponents, so no negative ones, and then no roots or fractional exponents, since they're the same thing, in the denominator, but they can be in the numerator. So for this one, I'll show you a couple ways to do this. First of all, I've got that negative here, so I could rewrite this as 1 over 64k to the 6th to the 1/3 power, which would then be, I could take the 1/3 power of the number inside, so 64 to the 1/3 power, and k to the 6 times 1/3, 6 over 3, which is k to the 2nd power. Now 64 to the 1/3, I'm going to need to think of as the cube root of 64, And since 64 is 4 cubed, that's going to be the cube root of 4 cubed, which is 4. So then I end up with 1 over 4k squared. Positive exponents, no rational exponents, so I am all set. You could also distribute, according to your exponent rules, that negative 1/3 to both of those terms right away. 64 to the negative 1/3. Okay, 6 times negative 1 over 3 is negative 2. And then, as with negative exponents, you can take those and move them to the bottom with positive exponents. And so you end up in that same place. You could also, from here perhaps, go ahead and say, well, that's my cube root of 64k to the 6th, if it's easier for you to think and work with radicals. And I'm going to go down so I don't crash into number 4. Right, that's going to be the cube root of 64 times the cube root of k to the 6th. If you want to, break those apart, and whatever helps you simplify those things out. Right, so that's going to be 1 over cube root of 64. Cube root of k to the 6th is k squared, since k squared cubed is k to the 6th. Okay, here on number 4, I'm going to simplify each one piece by piece. So, following my exponent rules, a squared to the 0 power is a to the 0, or 1. Right, 2 times 0 is 0. Then I'll simplify this one. A squared to the 1/2 power, I can multiply those. That's a to the 1st power. You could also think that's the square root of a squared, which is simply a. And then this one, why don't we go ahead and move it up, since it's 1 over a to the 1/2 power. So we could rewrite it up here, a to the 1/2. Alright, so that's going to be a to the 3 over 2. Or if you rewrote this as, you could also say that's a times root a, or a root a. Either one is fine. Here, if you wanted to write that as a cubed, square root, those are all equivalent. Moving on to numbers 5 and 6. Okay, so we're looking for ways to simplify this. We also don't want that root in the denominator. I'm seeing 24 and 30 share a factor of 6, so I think we can simplify this first. So, incidentally, root 4 simplifies nicely, and 3 and 30 I could break into 5 times 6. So root 4 is simply 2. Root 6 and root 6 cancel out, right? So that is equal to 1. And then I have 3 and root 5 left on the bottom. And then I need to make my denominator an integer without any roots. So then this is 2 root 5. And then in the bottom, 3. And then root 5 times root 5 is 5. So 3 times 5 is 15, and that's as simple as this one gets. Over here, different ways to think about it. If you're comfortable with rational exponents, the cube root of p is p to the 1/3. And in order to get a non-fraction exponent of p, I would need to multiply this by p to the 2/3, because 1/3 plus 2/3 is going to be 3/3. And I'll multiply this by p to the 2/3 over p to the 2/3, since that's 1. And I'll get 6p to the 2/3 over p to the 3/3, which is p. And this is going to be 6. I can simply rewrite the bottom as p. Okay. If you wanted a radical instead of a rational exponent, you'd have 6 cube root of p squared, and all of that over p. If you work with radicals from the beginning, you might think of it this way, cube root of p. Well, I need to multiply by whatever it takes to turn that into something that simplifies down to a number that doesn't require a radical. So if I had p cubed inside, right? Cube root of p cubed would give me p. So in order to get p cubed on the inside, I'm going to have to multiply this by the cube root, right? So same type of root, but p squared. So cube root of p squared. And that's the same thing I did over here, right? P to the 2/3. And that's going to give me 6 cube root p squared over cube root of p cubed, which is the same as that. Okay? So moving on to the other side. Simplify. We're looking for perfect squares in here. So we've got the 5 on the outside. 75 contains 25, right? That's 5 squared. It's 3 times 25, so I've got 3 left in there. I've got x squared and x from x cubed, so I can take out x squared since we're looking for square roots that simplify. So then root 25 is 5. I've got root 3 here. Root x squared is x. And then I've got root x. So if I put those together, I have 25x. And I can put these back together. I've got root 3x. Right over here, I'm looking for perfect cubes. I don't have any in them individually, but I have a 3 and a 5 from 15. And then over here, I've got cube root 3 times cube root 3, or cube root 9. Right, because 45 is 9 times 5. So that's where that came from. So here's 15. 45, you could think either of those two ways. In any case, whether you see, okay, I've got 3 threes, right, so 3 cubed, or you think, well, I've got 3 and 9, and that's 27, which I know is 3 cubed. Either way, that will simplify to simply the cube root of 3 cubed, which is 3. I've got 2 5s, but not a cube, and so that has to be expressed simply as the cube root of 25. Alright, so similarly over here, I have this one that can simplify as at the n squared. Square root of n squared is n, so that's simple. Then I've got root 5 and root 3. Over here, this is 4 times 5, so root 4, root 5, and root n all multiply together. Root 4 simplifies to 2, and I've got root 5 and root n. Root 5 times root 5 is 5, so then I have n times 5 from these two. I'm left with, I'll flip these around, 2 and root 3 and root n, so I can multiply that out to 10n, and this I can say more simply as simply root 3n. Okay, over here, root 5 on top, 20 is 4 times 5, and root 4 simplifies to 2, so I can write that out, root 5 over 2 root 5, and root 5 over root 5 is 1, so this is simply 1/2. Or you could have done this as, right, put that into 1 root 5 over 20, which simplifies to root 1 over 4, which is root 1 over root 4, which is 1 over 2. Alright, now, remember I can't add 45 and 5. This is not root 50, any more than I could say this is true. It's not, because this is 1 and this is 2, and 1 plus 2 is not root 5. It's 3. Alright, but what I can do is simplify this to 3 root 5 plus root 5, which gives me 3 plus 1 times root 5, or 4 root 5. Similarly, with this one, 3. 2 can come out, right? 8 is 4 times 2, and root 4 is 2. And then over here, 3 can come out, because 18 is 9 times 2, and root 9 is 3. So I have 6 root 2 minus 6 root 2. Right, for the same reason, 6 minus 6 root 2 is 0.